Welcome back to The Explainer. Today, we're diving into a theorem you probably met in calculus, but you might not realize just how powerful it really is, the mean value theorem. And to really wrap our heads around it, let's start with a puzzle, a real-world scenario that seems to defy all logic, but, as you'll see, is perfectly explained by this one elegant mathematical idea. So, picture this. You're driving down the highway. You see the cameras, sure, but there are no radar guns, no cops clocking your speed. You're super careful to be driving at the speed limit every time you pass one. And yet, a few weeks later, a speeding ticket shows up in the mail. How is that even possible? Well, here's how it goes down. An automated system clocks your license plate as you enter a 5-mile stretch of road at exactly 11 a.m. Then, just 4 minutes later, a second camera catches you leaving that same 5-mile stretch. And that's all it needs.
Here's the simple math the system did. You traveled 5 miles in 4 minutes. If you punch that into a calculator, it turns out your average speed over that distance was 75 miles per hour, well over the 65 mph speed limit. Now, your first reaction might be to fight, right? You'd say, wait a second, you never actually clocked me going 75. My speedometer never even hit that. And this is where the prosecution brings out its star witness, the mean value theorem. It's the piece of evidence that proves without a shadow of a doubt that your argument just doesn't hold water. To see why that ticket is totally legit, we need to get to the very heart of what calculus does. It gives us two different but related ways to talk about speed, or really any kind of change. And the mean value theorem, well, it's the bridge that connects them. On one hand, you've got the average rate of change. You can think of this as just the slope of a line connecting your start and end points. It gives you the big picture of your trip. But on the other hand, you have the instantaneous rate of change. That's your exact speed at one precise moment in time, which is the slope of the tangent line right at that single point. So here it is, the mean value theorem. And it makes a really simple, but honestly, a profound guarantee. For any smooth, continuous trip, no teleporting or anything crazy, there has to be at least one single moment where your instantaneous speed, your speed on the speedometer, is exactly the same as your average speed over the entire trip. And that, right there, is the airtight logic behind the speeding ticket. The theorem proves, it absolutely guarantees, that if your average speed was 75 miles per hour, you must have hit exactly 75 at some point, even if it was just for a split second. It's a mathematical certainty, and it's precisely why these average speed camera systems are used and legally upheld in places like the UK and Australia. Okay, so here's where things can get a little confusing if you're digging around online or in a textbook. You might hear people talk about two mean value theorems. So what's the deal? Are they the same thing? Well, not quite. What we've been talking about so far is the mean value theorem for derivatives, which connects the average slope to the instantaneous slope. But there's also an MVT for integrals, which is often called the average value theorem. This one says the total area under a curve is equal to a rectangle whose height is the function's value at some specific point. So one is about slopes and the other is about areas, or the average height of the function. Someone on Reddit actually put it perfectly. There are two distinct theorems that are basically saying the same kind of thing but from different angles using different tools. They're like two sides of the same beautiful coin, and they're deeply connected by another giant of calculus, the fundamental theorem. So, okay, it's great for writing speeding tickets, but why is this theorem such a big deal in mathematics? Why does it get its own chapter in practically every calculus textbook? It's because the MVT is what mathematicians call a workhorse theorem. It's not always the star of the show, but it's in the background doing all the heavy lifting that makes so much of the rest of calculus actually work. Think about it like this. A lot of the rules we just take for granted in calculus, they're all built on the logic of the MVT. That simple idea that a positive derivative means a function is going up, you need the MVT to prove that. The fact that a zero derivative means a function is constant? Yep, that's the MVT too. It's even a key step in proving giants like the fundamental theorem of calculus and Taylor's theorem. Let's wrap this up with something really cool. A fascinating question that takes this whole idea right to the edge of current mathematical research and shows just how deep this simple theorem really is. So remember how we had those two different MVTs, one for derivatives and one for integrals? Well, some mathematicians asked a brilliant question. Are there any special functions out there where these two theorems always point to the very same spot? When does the point with the average slope always happen to be the exact same point with the average value? And the answer is just so elegant. This special property, where the two means always land on the same point C, is only true for two types of functions: straight lines and exponential curves. That's it. Out of all the infinite functions in the universe, just those two. And that just makes you wonder, right? It shows that this seemingly simple theorem holds this deep, hidden secret about the nature of change itself. It's this beautiful link between the entire journey and one single perfect moment. And it leaves you with this question: what other hidden connections like this are just out there waiting for us to find them?